This is going to be my demo for Target 9D. I can design finite state machine counters, both synchronous and asynchronous. Right now I'm going to be going over the design process for synchronous. So first I started with a state diagram, and I wanted my counters to cycle through even numbers going up to 14. For this I chose to use a D flip-flop. And here I just laid out all my present states, going all the way down, and then from 0 I wanted to go to 2. And that's going to be the same pattern all the way down. And then from there, I put down my needed inputs. And I'm going to be using 4 different D flip-flops for this. So that's why there's a D0, D1, D2, and D3. And then for all of these, it's a lot smaller, but if D is 1, then it'll store a 1, and if D is 0, it'll store a 0, and it'll reset. So for each of these columns, so for example, for D3, I looked at Q3 and then the next state for Q3. So this is a 0, 0, so there's no change. So I'm gonna have our input be a 0 to accomplish this change. And then I just continued that. So for D2, this is 0, this is 0, 0, so it's a 0. And then for D1, here I'll go to one that changes. So for right here, to go from 2 to 4, our Q2 would need to change. So that's why there's a 1 for Q2 here. So taking all of that, I made K-maps for each of these D inputs, which are found right here. And then from the K-maps, I derived the Boolean equations. Some of them were simple. The D0, I saw that it just stays 0 the whole time, and that makes sense because all of these are even numbers. So the least significant figure should never be a 1 in this case. So yeah, there's that. Some of them got a little bit complicated, and we'll see that in my schematic. I tried to reduce my Boolean equations down a little bit, but they still ended up being pretty lengthy, as you can see. So I ended up just sticking with the original equations just to mitigate any errors that I could have made, because I haven't done Boolean algebra since we've learned tools to kind of bypass these. But yeah, this is going to be my design process for my synchronous counter. And then in the second video, I'll go through my actual implementation of it. But right now we're also going to go through my asynchronous counter. And for this, I wanted the same exact thing. I wanted to see, like which one was different, which one was not, or which one was more difficult. That state diagram, I can basically just go to that one for my state diagram. So right here, it ended up being way more simple because it's a pretty uniform pattern. So as mentioned previously, the least significant figure never changes, so I still hooked that up to ground. And then that still serves as my least significant output. And then I started the count, like the actual flip-flops, starting in the second bit. So we'll see in a little bit when I demonstrate, but the clock is actually hooked up to Q1. And then I realized that Q2 only toggles after 1 is down, or after Q1 is high. And then right here toggles again, right here toggles again. Furthermore, Q3 only toggles after Q1 is done being high. And then it only toggles that once. So this made for a very simple design. If I used a trigger edge, a negative trigger edge, I didn't actually have to do anything different to any of the inputs for the clock. So awesome.